In this video, what we're going to do is talk about the model that we have for the magnetic force. So what we do is we go out and we have charges moving around in magnetic fields, and we measure how their momentum changes. And by doing that, what we have found is that the force that acts on a charge that's moving in a magnetic field is given by the charge itself times the velocity that the charge has crossed into the magnetic field that is due to all of the other charges that are around that are moving. So what we can think about this is that this first part here, Q times V, has to do with the charge that we actually care about, the thing that's moving in the magnetic field. And this guy is external to that charge. So it's all of the magnetic field that's a result of all the other charges that are moving around and generating magnetic fields and so forth. And this is an interaction. It has to do with an external situation acting on a particular thing that we're looking at, and thus it gives rise to this force. So let's get a sense of what that actually looks like. So first of all, let's decompose this a little bit into its pieces. So this guy is the charge that is actually moving. So this Q includes the sign and size of the charge. The velocity here is the velocity of that moving charge, including its direction. Now, the magnetic field here is the one that is external to the rest of the situation that we have. So this is the external magnetic field. So again, the first two pieces of this, the charge and the velocity, have to do with the specific charge that's moving in the magnetic field. And the magnetic field here is the external one, the one that is not due to the charge that is actually moving. It's due to all the other stuff that's around it. So we can make a little bit of sense of this, right? So if, for example, I have some charge here, let's say it's a positive charge, and it's moving to the right. In that situation, if there's a magnetic field applied, then this charge is going to feel a magnetic force. It's going to experience a push or pull due to its interaction with the other charges that are producing the magnetic field. So in this case, what we'll do is we'll say that there is some magnetic field that's sort of all over, that points into the board, again due to charges somewhere else. And so we can actually calculate what this magnetic force is that this charge would experience. But what's important for us is actually to determine what the direction of that force is going to be. So looking at this cross product, what we have is something that is going to start with the direction of the velocity. So we'll point our fingers in the direction of the velocity. We'll curl our fingers into the magnetic field through the smallest angle, so into the board like this. And what we find is that that magnetic force pushes the charge upward. So as you can see, in this case, the force is perpendicular to both the magnetic field and the velocity vector. That is the result of this cross product situation. So the plane that's defined by the magnetic field and the velocity vector, that force is going to be perpendicular to that particular plane. So in a situation where this charge were negative, we would still do the same cross product. We'd have V cross B. But with that minus sign, we flip the sign. So a negative charge is going to be pushed downward. Right? So it turns out that these magnetic interactions can distinguish between positive and negative charges. That's quite useful. It'll come into play later on when we're working with different kinds of applications. So one other thing to pay attention to here is that we can actually calculate the magnitude of this force by considering just the relative orientation of the velocity vector and the magnetic field vector. So if you were to take this magnitude, you would be taking the magnitude of QV cross B, which is going to just give you the magnitude of the charge, so no sign anymore, the magnitude of the velocity, so just the speed, the magnitude of the magnetic field, times the sine of the angle between the velocity vector and the magnetic field vector. So you can see when the velocity vector and the magnetic field vector are perpendicular to each other, you get the sort of maximum amount of magnetic force. When they're parallel to each other, you get no magnetic force. So charges that move along the magnetic field direction experience no push or pull due to the magnetic interaction. So those are the two extremes, and then everything in between is just a little bit larger or smaller depending on what you're looking at. So the last thing I want to do is just make sure that we're understanding about this direction associated with the magnetic field and the magnetic force. So let's do one more example of that. So in this case, what we're going to do is we'll have a charge, and it's moving in this direction. And now I apply some magnetic field. Let's say everywhere in space, the magnetic field points like this. So kind of like that, right? So what's the direction that the force is going to point? Well, we have to know what the sign of the charge is, because V cross B points out of the board, but depending on the sign of the charge, it might point out of the board or into the board. In the case of this being a negatively charged particle, we would say it's V cross B, and then flip the sign so that the force that acts on this particle pushes the charge into the board. So what we've done in this video is introduce this model of the magnetic force, how it depends on the charge properties, so the charge itself, including its sign, the velocity of the charge, and then how it depends on the external magnetic fields due to other charges or currents that are producing that. And then we talked a lot about the direction and how we determine that, because that's one of the most useful things to help us understand how to work different kinds of applications.